Hello everyone, welcome back to TY Tech. And today we're going to talk about PVD and lead-off. So here is a picture for sputtering. So we sputter the argons to a target, then it will inject the target atoms onto the substrate, which is the wafer, to do the depositions. So like as usual, we'll first go through one page and give an overview about everything. Then we'll go to each step by step in detail. So PVD, physical vapor depositions. It was deposits a film growth achieved by accumulating a vapor onto a cooler substrate. In here, it will be wafer. Two ways to do the depositions. First is evaporations, which we boil up the molten metal and make it evaporate on the wafer substrate. So there are several factors will affect the evaporation. So we can see pictures over here. If we have a source over here, it will start heating up the source and to evaporate on different wafers. Okay, so one of the factor will be the distance between the source and the wafer. The other will be the angle between the, let's say we got a plane source over here. The angles between here and here will affect the thickness also. And also because we have two types of source, one is point source, the other was plane source, and most of the time it will be plane source. So the angles that caused by the source will also affect the result, which will cause the thickness on the each wafer will be quite different. So they figure out if we put a source from the middle to the end of the circle, which can make all the thickness in constant. Yeah, so that's one way to solve it, but this only directly works. And there's other factors might affect PVD, including the rate of impingement. So for the rate of impingement, it's per square per second area about the molecules that reach the surface. So how will affect this include the pressure. If you increase the pressure, you increase the rate of impingement, more molecules to do the depositions. If you increase the molecules mass, it will decrease the impingement rate. Also, there's another concept called mean-free path. It's an average distance between two molecules travel before they collide each other. So we want this parameter as high as possible. So if we decrease the pressure, we'll increase the mean-free path. That's why most of the time we will need to vacuum our tool. Also, if we increase the temperature, it will also increase the mean-free path. So for evaporation, there's a special process called lift-off. So for lift-off, what we want to do is we want to deposit metal over here only. So we can see PR will be the sacrifice layer. So we put the PR first, then we do the depositions, then we get rid of a PR. And here will be the only area that have deposited the metal. So we can avoid etchings, which will cause contamination or even over etch the device, cause the issue. And it will be simple process. For another ways to do the depositions will be sputtering. So for sputterings, it's like the first page we see, we sputter the argon or other molecules to hit on the target, then it ejects the atom and deposits on the wafer surface. Several key factors affect sputtering, including the incident angle of the argons, or even the energy of the incident atoms, and also the target material also affect the sputtering yield. And there's another concept called stack coverage. So as we can see here is a point source. If we do an evaporation, what will cause is this area, and this area. Due to the geometry of the surface, the wafer, it might not be really have the depositions or even depositions not enough. Several ways to avoid this. First is we can use sputtering to solve the issue, because evaporation will have better directional, but sputtering will be like more isotropic. And also you can heat up the wafer, you can rotate the wafer or add more point source. or you can increase the distance between the wafer and the point source, or you can use CVD or ALD to solve the issue. Okay, so that's the overview for the PVD, and we'll go into the details step by step now. So let's go for evaporations. So it's a film growth achieved by accumulate the vapors onto the wafer substrate. So as we can see here, here is a metal and we heat it up to do evaporation. Then it will hit onto the wafer surface. In here we put a wafer upside down to avoid any contaminations. Several factors will affect these mechanisms, including the rate of impingement, which is per area per second how many molecules can reach the wafer substrate. Increased pressure will increase the impingement rate. Increase of mass will decrease the impingement rate. Also, for mean free path, the travel distance between two molecules before they collide each other, and this will affect by pressure. Decreasing the pressure will help to increase the mean free path, or we can increase the temperature to increase the mean free path. Another factor will be vapor pressure over here. As we can see, that says if we want to deposit aluminums, we'll use tungsten as a carrier to carry this substrate because it has higher vapor pressure, harder to evaporate. And we can see over here, sodium have really high vapor pressure, meaning that it will evaporate it really easy, which will easy to cause the contamination during the process. Also, for the thickness of the wafer, that says here and here, it will affect by first is the incident angles of the point source to the wafer. Also, the distance will also affect the result. Also, the type of the source, point source and limited plane source will have different result. For the limited plane source, T2 will be T1 cosine theta. So this is a angle. So one way to avoid those parameters will be that you put a point source area to this location, which of the thickness will be constant by the equation over here. Next, we can talk about contamination issue. So there's a couple, for example, residue gases, and this is caused by insufficient vacuum initially or leaking, or even outgassing from the chamber wall. And how will it impact? If we have 1 microtorr of oxygen, which will result in impingement rate of 1015 oxygen atom per centimeter square, it will highly increase the resistivity of the device. So we can see here, if we increase the oxygen pressure, we can see the resistivity increase. Annealing can help, but if there's too much oxygen pressure to form the Al2O3, then it's too late. It will affect the resistivity tremendously. Solutions to avoid residue gas include pump down to lower pressure initially, or fill up the chamber with argon and pump down again to dilute the remaining gas. Also, there's other techniques include thin film adhesion. Sometimes we'll add thin films onto the substrate to promote the adhesion. So titanium and chromium is the common adhesion layers. Then we will talk about lithof. It's a process to enable to pattern the metal without etching it directly. So photoresist was used as a sacrifice layer. So in here, we'll first put a PR, then we deposit some metal on it. Then we get rid of a PR, we do a PR strip, and this is the only area we have deposited some metal. So in the past, what we will do if we don't use lithof, it will be like we will first deposit the whole areas of the metal. Then we put a PR on here. Then we do an etching for these two plates. Then we strip off a PR. And it will be more complicated process. So therefore will be simpler process and we don't need etchings, which can prevent damage or contamination by the metal etchings. And it is also suitable for the metal that is really hard to etch. next we'll go talk about sputtering. So for sputtering, we got anode and cathode to induce a plasma, and argon will hit down to a target to let the atom injected on the wafer substrate. So sputtering yield is defined as incident ions, which is argon over here, and the atom injected, which is a target over here. So incident angles and the incident, so here's the incident angles, will affect the sputtering yield. Incident of ion energy, so if we increase in the ion energy, it will also affect the sputtering yield. So sputtering rate will also difference between the material over here. Okay, so there's non-reactive sputtering and reactive sputtering. So for non-reactive sputtering, sputtering gas will not incorporate to the films. So common choice will be argon. Reactive sputtering is sputtering gas will incorporate to the films to form that silicon oxide, aluminum oxide. So common choice will be oxygen or nitrogen. And we can see over here, this is for sputtering and this is for evaporations. We can see sputtering is more energetic compared to evaporate. So it will have better film adhesion and also better stack coverage. And we'll talk about stack coverage on the next page. However, it is slower and worse directional, so it will be bad for lid-off. So what's stack coverage? In here, we can see if we have an evaporation from this location, if we are going to do a sputtering, this area might not be deposited enough or even won't be deposited due to the geometry of a wafer. Several ways can improve this include you rotate the wafer, or you can increase the source to wafer distance. So your Duke side from every location will be like 90 degrees injected. Also, you can use multiple evaporation source, or hit down the wafer, or switch to sputtering because it is not directional, or even switch to CVD or LD. And that's it for all the PVD part. Thank you.